Hello students, today we will see the theory part 4 of the chapter 9 hydrocarbons, in which we will cover the NCERT section 9.2.3. So this is our disclaimer. After attending this lecture, you will be able to understand the chemical properties of alkane. So we have already dealt with the physical properties and with the preparation of alkanes. Now we are interested in knowing the chemical properties of alkanes. Then if I talk about the specific name of the NCERT section that we are going to cover, so we are going to cover the 9.2.3, which is property of alkanes, specifically the chemical ones. Doing this will help us to know the chemical reactions that an alkane can undergo. Then after, we will summarize our today's lecture with a short note. Let us begin our discussion on chemical properties of alkanes. So alkanes are relatively less, I would say, less reactive as compared to the alkenes and alkynes. So basically, this is due to the strong C single bond C and C single bond H. Okay. As a result of this, if you are comparing the reactivity of alkanes, alkynes, and alkenes, then alkanes are the least reactive. Then after, another important feature of alkane is their non-polar nature. So this non-polarity means alkanes do not have a positive or a negative end, which contributes again to their unreactivity. They don't mix well with the polar solvent like water, similar to how oil and water don't mix. Despite their unreactive nature, alkanes can undergo reactions, but only under specific conditions. This means that certain factors like high temperature or the presence of a catalyst are needed to initiate reaction regarding the alkanes. So here we have some reactions of alkanes. First, we have the substitution reaction. Then next we have combustion. After that we have this controlled oxidation. Then isomerization, aromatization, also known as reforming. Then we have reaction of methane with steam, which is known as steam reforming. And lastly, we have pyrolysis, also known as cracking. So these are the 7 methods or 7 chemical reactions of alkanes that we are going to address today. So let us first start with the topic of substitution reactions in hydrocarbons. Now we see that in alkanes, hydrogen atoms can be replaced by other atoms of group. So this is the basis of your substitution reactions. The first group that can replace hydrogen atom in alkane is halogen. So you know halogen, they can be chlorine, bromine or iodine. Next we have the nitro group. So the nitro group is represented by NO2 and it can also be replaced by hydrogen atoms in alkanes. Finally, we have the sulfonic acid group represented as SO3H, which can also substitute hydrogen atoms in alkanes. Continuing our discussion on substitution reaction of alkanes, now we are introducing free radical halogenation, a type of substitution reaction. So this process involves the reaction of alkanes with halogen. It is important to note that this reaction requires specific condition to occur. Alkanes react with halogens at high temperature between 573 to 773 Kelvin or in the presence of ultraviolet light. This condition provides the energy needed to break bonds and initiate the reaction. Let's look at a specific example. Suppose we are considering the chlorination of methane. In this reaction, methane reacts with chlorine under UV light to form chloromethane and hydrochloric acid. So this is a classic example of substitution reaction where one hydrogen atom in methane is replaced by another chlorine atom. So continuing with the chlorination process, your chloromethane, which is CH3Cl, can be further reacted with chlorine to form dichloromethane, CH2Cl2 and hydrochloric acid. This shows how multiple substitution can occur leading to different products. the reaction can proceed even further, where your dichloromethane CH2Cl2 can further react with chlorine to form trichloromethane and hydrochloric acid. Each step involves replacing another hydrogen atom with a chlorine atom. So, finally, trichloromethane, which is CHCl3, it can also react with chlorine to form tetrachloromethane and hydrochloric acid. This series of reaction demonstrates how a single alkane can undergo multiple substitution to form various chlorinated products. It is important to note that a mixture of product is formed during these reactions. This means that different chlorinated compounds can be produced simultaneously depending on the reaction condition and the extent of substitution, right? Continuing with this substitution reaction, now we'll move on to the detail. So next is free radical halogenation. So we talked about this, now we'll talk about its mechanism. If I tell you about the reactivity order of halogen, so this tells us how different halogens like chlorine, chlorine, bromine and iodine react in free radical halogenation. Fluorine is the most reactive, followed by chlorine, bromine and iodine. So this order is important because it helps us to predict which halogen will react more readily with alkanes, right? Here we have the reactivity of alkane based on the type of hydrogen atoms involved. Tertiary hydrogen are the most reactive one, followed by the secondary, then primary hydrogen. This means that in a molecule, the hydrogen atom attached to a carbon with other three carbon neighbors are more likely to be replaced by a halogen. Okay. Moving on further in this free radical halogenation, now we will talk about the mechanism of the free radical chain reaction. So, the term initiation appears marking the step in the free radical chain reaction. So, this step is crucial as it starts the entire process. In chemical reaction, initiating is like lighting a match to start a fire. Here we learn that the chain is initiated by the homolysis of chlorine gas in the presence of UV light. Homolysis is when a bond breaks evenly and each atom takes one electron, forming free radical. So this is similar to how sunlight can cause certain reaction to start, like how UV light can cause sunburn. The chemical equation for the initiation step is chlorine gas absorbs UV light, causing the bond to break and form two chlorine free radical, which is Cl dot. So these radicals are highly reactive and will drive the next steps of the reaction. Continuing to study the mechanism of free radical chain reaction, next we will focus on the propagation step of the free radical chain reaction. Propagation is the stage where the reaction continues to produce more radicals, allowing the reaction to sustain itself. In this step, a chlorine free radical attacks a methane molecule. This attack breaks the carbon-hydrogen bond in methane, resulting in the formation of a methyl radical. Now, the chemical equation for the reaction we just described. So, CH4 gas react with a chlorine radical in the presence of light to form methyl radical and hydrogen chloride gas. So, this is a classical example of propagation reaction. Now, the newly formed methyl radical is ready to react with another chlorine molecule. So this is the key part for the propagation process, where the radical continues to react with stable molecules to form new radicals. So this is basically formation of more and more radical. Therefore, we are calling it as propagation process, where your radical is propagating. In this reaction, the methyl radical reacts with a chlorine molecule to produce chloromethane and another chlorine radical. Now, we can see that in each of the propagation step, you have a radical in the reactant side and you have a radical on the product side. If you compare this thing with the previous reaction, which is initiation, there we can see that on the product side only we have the radical, on the reactant side we have a stable molecule. So in this way you can just differentiate between propagation, initiation and the next upcoming step, which is termination. Now this will lead to the formation of chloromethane CH3Cl. Now the Cl dot radical, which is regenerated here, you can see that we have a chlorine radical in the B reaction. It continues the chain and many other propagation steps are possible due to this leading formation of chlorine radical, right? Let us move on further in the mechanism of free radical halogenation. So we have our last step, which is termed as termination. So this refers to the stage in a free radical chain reaction where the reaction comes to an end. What will happen? The chain stops when two radicals combine with each other to form a stable molecule, effectively halting the reaction process. So we can have specific parts of this. So the three parts of this are given here. There can be a case where two chlorine radical can react and give a chlorine molecule. There can also be a case where two methane radical can react and form a ethane molecule, and one methyl radical and one chloride radical can react to form chloromethane. Now, in each of this given termination step, you have a radical on the left hand side, but no radical on the right hand side. So, this is the identity proof that the given reactions are termination. So, we can just summarize the identity proofs. For initiation, we have only the radical on the right hand side, that is on the product side. For the propagation, we have radical on both reactant and product side, and for the termination, we have it on the reactant side only. Got it? Finally, we see that ethane is also mentioned in the product, so it can be considered as the byproduct of this reaction. So the main reaction is giving us chloromethane, and we are getting ethane as the byproduct or the secondary product. Now this can also be useful in industrial application like fuel or as a building block for other chemicals. Let us now start with the topic of identifying the steps in free radical halogenation. So, if I talk about the initiation step, then the initiation step will always generate radical. So, radicals are highly reactive species with unpaired electron, we know that, and they play a key role in driving the reaction forward. So, we call it as the initiation step. The product side of the initiation step contains two free radicals. This is important because it shows that the reaction has successfully generated the reactive species needed for the next steps. After that, we have an example here to explain the same. The chlorine gas undergoes homolysis, which means the chlorine-chlorine bond breaks evenly, forming two chlorine free radicals. Next, we will move on to the propagation step. So, this step is where the reaction continues to progress by involving radicals reacting with stable molecules. In the propagation step, one radical reacts with a molecule to produce another radical. So, this keeps the chain reaction going on. So, on the reactant side, we have one radical, and on the product side, we have also one radical. So, this balance is crucial for the continuation of the reaction, ensuring that process can repeat repeatedly. The chemical equation for the propagation of the step is shown here. So, methane is reacting with chlorine radical to form methyl radical, so which is a radical again, and hydrochloric acid. So, this is like a relay race where the baton or the radical is passed along to keep the race going on. Continuing with the identification of the step in the free radical halogenation. Lastly, we have the emphasis on this termination step. So, in this step, radicals are always removed by combining them. How? Always remove radical by combination. The next point highlights that the reactant side having two radicals while the product side has no radical. So, this means that the radical have combined to form a stable product, effectively ending the chain reaction. Here we see a specific reaction of termination step in a chemical equation. Chlorine radicals are combining to form chlorine gas. So, this is a simple yet important reaction that helps us to understand how radicals are neutralized. Now, we are going to discuss the combustion of hydrocarbon. So, alkanes when heated in the presence of excess air or oxygen undergo combustion to form carbon dioxide and water. So, this reaction releases a significant amount of heat, similar to how burning wood generates warmth. Now, let us look at an example of this combustion process to better understand how it works in practice. Here is the chemical equation for the combustion of methane. Methane is reacting with oxygen to produce carbon dioxide and water, releasing 890 kilojoule of energy per mole. So, this is a typical exothermic reaction, meaning it releases energy. How much energy it releases? It releases minus 890 kilojoule per mole of energy. Another example is for the combustion of butane, whose production is 2875.84 kilojoule per mole of energy. So, butane again reacts with oxygen to form carbon dioxide and water. What you can see here, that the number of carbon atom is increasing, is indicating at the same time that the amount of energy released has increased. Okay, because the first one is releasing 890 kilojoule and the second one is releasing approximately 2875 kilojoule of energy for per mole of butane. Got it? Now, we can write a general equation for the combustion of any alkane. So, this will help us to do numerical problems as well in the thermodynamics. The general equation for the combustion of alkane shows that an alkane whose formula is CnH2n plus 2 reacts with 3n plus 1 by 2 of oxygen to produce n moles of carbon dioxide and n plus 1 moles of water along with heat. So, this equation helps us to predict the product and energy released for any alkane combustion. Now, we are starting our discussion on incomplete combustion, which is a type of chemical reaction again. So, this process is important to understand because it occurs when there isn't enough oxygen available for a fuel to burn completely. Let us focus on what happens during incomplete combustion. It occurs when there is a limited supply of oxygen. This means that the fuel does not burn completely, which can lead to different products being formed compared to the complete combustion. So, we see a chemical equation here representing incomplete combustion. So, methane gas reacts with oxygen gas to produce solid carbon and water. So, this is different from complete combustion where carbon dioxide would be the product, and this reaction is similar to what happens when a candle burns with flickering flame due to insufficient oxygen. So, you must have seen, if you put a piece of paper or if you put a tin or a utensil above the candle, you will see that black sooty flames are deposited on your utensil or on your container. It means that that thing is carbon black, that contains carbon black, and it is depositing due to the incomplete combustion of carbon, as you are stopping the, I would say, amount of oxygen supply. So, as a result of this incomplete combustion, your carbon black is formed. So, this is a fine black powder that has various uses. It is used in making ink, black pigments, and printer toner. It is a practical example of how incomplete combustion products can be utilized in everyday applications. So, now let us study about this controlled oxidation in hydrocarbon. This involves understanding how alkanes react with oxygen under specific condition to form various products. Alkanes, when heated with a regulated amount of oxygen and a catalyst, can form different oxidation products. So, this process is controlled to achieve specific outcomes. Here, we see an example of methane reacting with oxygen in the presence of copper as a catalyst at 523 Kelvin and 100 atmospheric pressure. This reaction produces methanol, a type of alcohol. It is similar to how certain industrial processes convert natural gas into useful chemicals. In this reaction, which you are seeing the later on, methane is reacting with the oxygen using molybdenum trioxide as a catalyst and heat, resulting in the formation of methanol, also known as formaldehyde, along with water. Now, this is also an example of partial oxidation, where all hydrogens are not replaced by oxygen. So, you can tell that in controlled oxidation, we do partial oxidation. Third, ethane react with oxygen in the presence of manganese acetate and heat to produce ethanoic acid, commonly known as acetic acid, and along with that we get water. So, this reaction shows how alkanes can be converted to carboxylic acid, which are an important part in the production of vinegar. After that, if you take 2-methyl propane and do its oxidation with potassium permanganate, then it will form 2-methyl propane 2-ol and alcohol. So this reaction highlights how strong oxidizing agent can convert alkane with tertiary hydrogen into alcohol. Got it? Now you can see that in all of these four reactions, we have used four different catalysts, and it results in four different type of products. Like we have alcohol, we have aldehyde, we have acid as well. Now metals such as copper, molybdenum trioxide and manganese acetate are used as catalyst to control the partial oxidation of alkanes. So this catalyst helps us in directing the reaction towards specific products by influencing the reaction pathway. Potassium permanganate is a very strong oxidizing agent, particularly effective in converting alkanes with tertiary hydrogens into alcohol. Now, why we are saying it tertiary? If you look upon 2-methyl propane, the carbon is attached to such a hydrogen which is a tertiary one. Why? Because to that carbon 3-methyl groups are attached. So the hydrogen attached to a tertiary carbon is a tertiary hydrogen, and it is very difficult to oxidize such hydrogens to alcohol. So we can consider that potassium permanganate is a strong reducing agent. Now in this section we are going to study the concept of isomerization, specifically focusing on how straight chain alkanes can be transformed into branched chain isomer. Straight chain alkanes are converted into branched chain isomer when they are heated in the presence of anhydrous aluminum chloride and dry hydrochloric gases, hydrogen chloride gases. So this reaction is a type of rearrangement where the structure of the molecule is altered without changing its molecular formula. Here we can see the example of that. So we have a reaction of N-hexane and we are doing it again in the presence of anhydrous AlCl3 and HCl. What we are getting is just an isomer of N-hexane. The first one is 2-methylpentane and the second one is 3-methylpentane. Here the product that you are seeing is not undergoing any change in number of carbon, only the isomer is being formed. If I ask you which kind of isomers are formed, then you can say that these are structural isomers, and 2-methylpentane and 3-methylpentane are specifically position isomers because here the position of substituent is changing from 2 to 3 of the methyl. Let us learn more about this isomerization. Now let us look at the mechanism of isomerization in that process. So this will help us to understand the step-by-step process involved in this transformation. So the first step in the mechanism is carbocation formation. Anhydrous aluminum chloride and dry hydrogen chloride acts as a powerful Lewis acid catalyst in this process. These catalysts help us to facilitate the formation of the carbocation. The carbocation intermediate is generated through the abstraction of hydride ion, which is a hydrogen atom with an extra electron from the alkane. So this step is essential for the formation of the carbocation. Then after, the process aims to produce more stable carbocations such as secondary or tertiary carbocations, which are more stable than primary ones due to their inductive effect on the carbon containing positive charge, right? The next step in the mechanism is rearrangement. So once you form the carbocation, the formed carbocation undergoes rearrangement. How? So basically, if you are getting a primary carbocation, then it will try to undergo rearrangement to form secondary or tertiary carbocation so that it can attain a stable condition. The carbocation undergoes rearrangement, which are structural changes that help stabilizes the molecule further. These rearrangement can include shifts of hydrides or alkyls. This shifts helps us in achieving a more stable molecular structure. And the final step in the mechanism is chain termination. So this step involves the completion of the reaction process. How we can see it? So basically the carbocation accepts a hydride ion from another alkane. Now this helps us to stabilize the carbocation and get a neutral molecule. As a result, the branched product is formed and a new carbocation is generated. This is an important step in the continuation of the reaction, and the process continues as the reaction chain goes on, where the newly formed carbocation can react further, perpetuating the cycle. This is how isomerization can lead to the formation of various branched hydrocarbons. Then after, we will discuss the process of aromatization, also known as reforming. So this is an important topic in the study of hydrocarbon. Aromatization is an industrial process where a straight chain is taken and it is being transformed into aromatic hydrocarbon. So this transformation is crucial in the production of chemicals used in various industries, and we can take some examples of it. Suppose we are doing it for the formation of benzene. Here is a reaction shown to do that. So if you take hexane and try to convert it into benzene, you have to do that at high temperature such as 773 Kelvin and high pressure which is 10 to 20 atm in the presence of a strong oxidizing agent such as Cr2O3 or V2O5 or MO2O3. So these all three are strong oxidizing agent. You can use any of them. N-alkanes with 6 or more carbon atom undergo dehydrohalogenation followed by cyclization when heated. So this means that hydrogen atoms are removed and the carbon chain forms a ring structure leading to the aromatic compound. The process of aromatization is carried out in the presence of metal like vanadium oxide, molybdenum oxide or chromium oxide, which are supported over alumina. So this metals acts as catalyst to facilitate the reaction. Now we'll move on to the next type of preparation method, which is reaction of methane with steam or steam reforming. Here, what will happen in the first part of this reaction, methane, which is a simple hydrocarbon, reacts with steam. So this reaction occurs at high temperature because steam is something which is always there at high temperature and it requires a nickel catalyst. The product of this reaction are carbon monoxide and hydrogen gas. Now this is similar to how catalysts are used in other reactions to speed up the process without being consumed. Here is the chemical equation for the reaction. CH4 plus H2O in the presence of a nickel catalyst and heat yields CO and 3H2. So this equation shows the transformation of methane and water into carbon monoxide and hydrogen gas, highlighting the stoichiometry of the reaction. This reaction is primarily used for the industrial preparation of the hydrogen gas. Next, we are going to study the process of pyrolysis, also known as cracking. So, what happens during pyrolysis? It involves the decomposition of higher alkanes into lower alkanes and alkenes when heat is supplied, and this is a crucial process in petrochemical industries. The term pyrolysis has its root in the Greek language. Let us study what the name signifies. So, the first part of the word pyro means fire, and this indicates the involvement of heat in the process. Then after, the second part is lysis, means breaking. So pyrolysis essentially refers to the breaking down molecule using heat. Now let us consider an example to better understand pyrolysis. This will illustrate how larger hydrocarbons are broken down. So here is an image showing a specific chemical reaction where it represents the process of pyrolysis, where a larger molecule like C6H14 is breaking down into simpler molecule. So at 773 Kelvin, it can give various combination of products like C6H12 plus OH2 or C4H8 plus C2H6 or C3H6 plus C2H4 plus CH4. Now this reaction specifically follows the free radical mechanism like the halogenation of the alkanes. This means that the reaction proceeds to the formation of free radical, which is highly reactive species. Now let us look at the application of pyrolysis. So this process is used in the production of oil gases and petrol gas from kerosene or petrol. Then after, it is used in the fragments. We see a specific example of pyrolysis reaction. So dodecane, a hydrocarbon with the formula C12H26 is broken down into heptane, C7H16 and pentane, which is C5H pentene, okay, not pentane, pentene, which is C5H10. This reaction occurs at even higher temperature, which is 973 Kelvin, in the presence of catalysts like platinum, palladium or nickel. And this process is similar to how a larger piece of wood are broken into smaller pieces when burnt, releasing energy and forming new substances. Let us now summarize our today's discussion. The first characteristic of hydrocarbon is that, if I talk specifically about alkanes, so they are unreactive in nature. This is because the strong carbon-carbon bond and strong carbon-hydrogen bond they have, which is difficult to break. Next characteristic is the hydrocarbons are generally non-polar. This means that they do not have a significant difference in the charge across the molecule, making them less likely to react with polar solvents like water. After that, we saw that the hydrocarbon needs specific conditions to react. This means that under normal circumstances, they do not readily undergo chemical reactions. Moving on to the reactions that they give, the first one is substitution reaction. So, in substitution reaction, a hydrogen atom in the hydrogen atom in the hydrocarbon is replaced by halogen such as fluorine, chlorine, bromine, or iodine. Next, if I talk about the reactivity, then F2 is the most reactive one. Then we have the chlorine molecule, bromine, and lastly the iodine. If I try to explain the reactivity in terms of hydrogen atom, which is to be removed, then the 3-degree hydrogen is the most reactive one. Okay. Then comes the 2-degree and then comes the 1-degree. But the difficulty is that with the fluorine, that your fluorine reaction is somewhat very much exothermic. So we generally don't do this reaction. Okay. Next, we have the combustion of hydrocarbons. So, in complete combustion, hydrocarbons react with oxygen to form carbon dioxide, water, and heat. This is similar to how gasoline burns in a car engine to release energy. If I talk about the incomplete combustion, then it occurs when then there is not enough oxygen, leading to the formation of carbon black, which is a form of soot. So, this can happen in poorly ventilated space and is a safety concern. After that, we talked about the controlled oxidation. So, we see that the first example of controlled oxidation is against the methane molecule, a simple hydrocarbon, which is converted into methanol using copper as a catalyst. So, this reaction involves adding an oxygen atom to methane, similar to how wood absorbs oxygen when it is burnt. Next example shows methane being oxidized to methanol, also known as formaldehyde, using molybdenum trioxide as a catalyst. So, this is another step in adding oxygen to methane, changing its structure and properties. Then after, we can convert ethane into ethanoic acid with the help of manganese acetate. So, this reaction is a bit more complex one, as it involves breaking and forming bonds to add oxygen, similar to how vinegar is made from alcohol. Last one, we have 2-methylpropane, which undergoes oxidation to form alcohol using potassium permanganate, which is again a very strong oxidizing agent. So, this reaction highlights how different hydrocarbon can be transformed into compounds through controlled oxidation. Next, we move on to the isomerization process. So, the isomerization can change your straight chain into branched chain hydrocarbon. We use AlCl3 and HCl for this isomerization process. So, this substances helps to facilitate the rearrangement of the hydrocarbon chain, making the process more efficient. Next, we have studied about this aromatization, which involves converting alkanes into aromatic compounds. So, in aromatization, alkanes are transformed into aromatic compounds, and the catalyst used for this aromatization includes vanadium pentoxide, molybdenum trioxide, and chromium trioxide. This catalyst helps us to facilitate the conversion of alkanes into aromatics, making the process more efficient and widely used in the chemical industry. Lastly, we talked about two more processes. The first one is steam reforming, where we have this chemical equation and the methane is reacting with steam to form carbon monoxide and hydrogen gas. This is an important industrial process for producing hydrogen gas. Here, nickel is used as a catalyst and it speeds up the reaction without being consumed up in the process. Lastly, we talked about this pyrolysis. So, basically, pyrolysis means breaking your larger hydrocarbon into smaller one. How do we do it? So, we simply heat our hydrocarbon, which is a longer chain, and we get a mixture of lower alkanes. Now, this process is not that much useful because it gives us a mixture of alkanes that are very difficult to separate, and this reaction goes through the free radical mechanism. This was all for today's lecture. Thank you for joining the session. I hope you enjoyed it.